Hello, the purpose of this video is to tell you not so much about Kepler's third law for elliptical planetary paths, but to take you through a series of mathematical steps in which I explain how to use a t-substitution called the Weierstrass substitution in order to get from the equation of path for an elliptic orbit to the well-known Kepler's third law for planetary motion. This treatment is particularly rigorous in its approach, and I designed this presentation to illustrate more so the mathematical approach taken to get to the end result, rather than to simply add to the many current explanations regarding already well-known and much explained features of the physical universe. In short, I felt that this particular derivation was lacking, not only on the web, but also in many textbooks and other literature that I have come across in recent times. I hope that it proves good. The equation of path in terms of velocity u and the angle phi through which the radial vector turns is governed by a second-order ordinary differential equation of a periodic nature from which we obtain an example of a radial solution and hence one in terms of u below on solving the ODE. Here, 1 over the square root of 2 is the eccentricity of the orbit. We know from Kepler's second law of areas that the rate of angular change is d phi by dt, which is equal to h over r squared, and in turn, this is equal to hu squared. So substituting this into the radial solution leads us to form the complicated integral for the whole ellipse over 2 pi radians, as stated at the foot of this slide. So, to solve the given integral, we use the trigonometric substitution. T equals tan phi over 2, where phi is the general angle through which the planet turns from its starting point. From this trigonometric expression, we can also obtain the relationships from forming a right-angled triangle for both sine and cosine, as well as a derivative dt in order to proceed further. I will avoid reciting the following trigonometric expressions that I obtained, but they are fairly standard and we will need these in the next 2 slides. We now introduce the double angle formula for both sine and cosine and substitute into them the trigonometric relationships stated on the previous slide. This results in a particularly vital expression in terms of t for the cosine of angle phi. Since we already deduced the derivative expression for d phi, also in terms of t in slide 4, we now substitute this and our cosine term into the original integral, again stated below. Note that we have set the eccentricity of the orbit to be equal to q over p, and so this factorizes out more easily and clearly to yield a much simpler to handle integral. We can see that the integral on the far right-hand side of the above is relatively straightforward, this being equal to an inverse tangent function. But the first integral is much more involved and needs to first be expressed in terms of partial fractions. We then use the trigonometric substitutions. T equals the square root of a times the tangent of s, and dt equals the square root of a times the whole of 1 plus tangent squared s times ds, whereby we obtain an even simpler integral in terms of cosine squared. We then use the familiar identity cos squared s is equal to a half plus a half cos 2s, and eventually obtain the following two versions of the solution. The latter in terms of both the sine and inverse tangent functions of both s and t respectively. Using the tangent substitution from slide 8 and the double angle formula, sine 2s is equal to 2 sine s cos s. On inserting each of these into the above last integral, after some manipulation, we obtain the general solution in equation 3 below. From slide 3, we now resubstitute t is equal to the tangent of phi over 2, and after further manipulation of the algebra, and after reinserting our actual values for both p and q, we obtain the following particular solution in terms of both the inverse tangent, the tangent, and sine and cosine functions. To obtain an actual value for this integral, we have to manipulate the limits as shown in both the inverse tangent and sine and cosine parts of the solution. This is because of the asymmetric nature of the tangent and sinusoidal functions and their graphs, and because the tangent is undefined at pi over 2. All we need to do to get around this problem of having to change the limits is to multiply the inverse tangent function by 4, which is the number of elliptical quadrants, and the sine and cosine part by 2, the number of elliptic halves, thus ensuring that we have now modelled one single planetary revolution to the tune of 2 pi, or 360 degrees, about its local star. On following through with the algebra, you will therefore see that the final numerical solution obtained is 4 times pi times the square root of 2, and this means that we have almost completed the proof. Equating 4 times pi times the square root of 2 with the right-hand side of the integral in equation 2 of slide 2, and after squaring both sides and again manipulating the expression, we therefore obtain Kepler's third law, in which we see that the cube of the average radial component r sub 0 is proportional to the square of the period big T. Note that I used r sub 0 here because I have already used the letter A for something else earlier on. That basically concludes the proof, but I hope that you have found this presentation both helpful and of value, and until next time, I bid you farewell for now. Well, thank you for listening.